Hey, welcome to The Explainer. Today we're going to dig into a huge idea in calculus, something that feels really intuitive but holds some seriously surprising power. We're talking about continuity.
We all kind of get what this means, right? An unbroken line is, well, it's a line with no breaks. It's smooth, it flows. But in math, a gut feeling just doesn't cut it. We need something way more solid, something we can really build on.
And this is probably where you started too, the good old pencil test. If you can sketch out the whole graph in one single go without ever lifting your pencil off the paper, then it's continuous. Sounds easy enough, right? But, yeah, it's not always that simple.
See, that whole pencil test thing, it really starts to fall apart when you get to the weirder side of mathematics. And if we're going to build the entire rest of calculus on this idea, I'm talking derivatives, integrals, the whole shebang, our foundation needs to be made of steel. It's time to upgrade our intuition.
So, here it is, the big one. This little sentence is the rock-solid definition of continuity. It might look kind of simple, but it's packed with meaning. It says that the limit, that's the value the function is heading towards as you get closer and closer to a point, is the exact same as the function's actual value right at that point. In other words, the place you are aiming for is exactly where you land. No last-second swerves, no mysterious holes.
All right, so let's unpack that a bit. It really just boils down to these three simple checks. First, the point actually has to be there. I mean, f of a has to exist. You need a solid dot on the graph at that spot. Second, the limit has to exist. This means as you come in from the left side and as you come in from the right side, you're heading toward the exact same spot. And third, this is the clincher, those first two things have to be equal. The point that's actually there has to be the same point you were heading towards. If you can check all three boxes, you've got continuity.
So, what happens when a function breaks one of these rules? Well, we call it discontinuous. But here's the thing, not all breaks are created equal. Let's get into the different ways a function can fail to be continuous.
First up, you've got what's called a removable discontinuity. Think of this as the easiest break to fix. It's like the line is perfect, but there's just one single tiny point missing, a little hole. The limit exists, everyone's heading to the right party, but when you get there, the door is locked, or maybe the house is somewhere else entirely. It's called removable because you could literally just fill in that one little dot and make everything continuous again.
Then there's the jump discontinuity. This is exactly what it sounds like. The function is cruising along at one level, and then, bam, it instantly teleports up or down to a completely different level. The limit coming from the left is totally different from the limit coming from the right. A great real-world example is tax brackets. You make one more dollar, and suddenly you're in a whole new bracket. It's a jump, not a slope.
And finally, we've got the most wild one of all, the infinite discontinuity. This is what you see at a vertical asymptote. The function just goes completely vertical, shooting off to positive infinity or diving down into nothingness. There's no fixing this, no plugging a hole. The gap is literally infinitely large.
Okay, so now we're going to see exactly why we needed that super strict three-part definition. Because we're about to look at some functions so weird, so mind-bending, that our friendly old pencil test is just completely useless.
Yeah, mathematicians literally call these pathological functions. And for good reason. They follow all the rules of math, but they behave in ways that just seem wrong, They completely defy our visual intuition, and they prove why we need a definition that doesn't depend on drawing anything at all. Okay, get a load of these two. On the left, Dirichlet's function. It's a total chaotic mess. It's equal to 1 if the number's rational and 0 if it's irrational. It's broken at every single point. You absolutely can't draw it. And on the right, the maze function is even weirder. It looks like a cloud of points, and it's somehow broken on all the rational numbers, but continuous on all the irrational ones. These functions show, without a doubt, why the pencil test just isn't enough.
All right, so we went through all that heavy lifting. The formal definition, the different types of breaks. Why? What's the payoff? Well, it's a big one. We get one of the most useful guarantees in all of calculus, the intermediate value theorem.
What this thing guarantees is actually incredibly simple but so powerful. It says that if you have an unbroken line that starts at one height and ends at another, you are guaranteed to pass through every single height in between. To get from a height of, say, 5 feet to 10 feet, you have to pass through 6 feet, 7.8 feet, and 9.99 feet. Basically, continuity means no teleporting. You can't just skip the values in between.
And look, this isn't just some abstract idea to impress your friends. This guarantee, it's a real tool that lets us prove that things exist, even when we can't find them easily.
It's actually the secret weapon behind a lot of the software we use every day.
Here's a perfect example. Ever wonder how your calculator solves some crazy-looking equation? It often uses this very theorem. Step 1, it finds one spot where the function is negative and another where it's positive. Step 2, because the function is continuous, the IVT guarantees that it must cross 0 somewhere between those 2 points. A root has to be in there. Step 3, the calculator just keeps cutting that interval in half again and again, trapping that root until it has it pinned down with incredible precision.
All right, for our grand finale, let's see how this super abstract math concept solves a problem that I know you've run into. That annoying wobbly table at a cafe.
This is amazing. The intermediate value theorem actually proves that if you have a square, four-legged table on any continuous floor, even if it's lumpy and uneven, you can always make it stable just by rotating it. Seriously. Mathematicians defined a wobble function. As you rotate the table, the wobble changes continuously. The IBT guarantees that at some point in that rotation, the wobble value must pass through 0. And a wobble of 0, that's a perfectly stable table.
And that's really the point, isn't it? Continuity isn't just about drawing lines. It's a fundamental truth about how our world works, one that gives us these powerful guarantees. It helps calculators find answers, it stabilizes our coffee tables, and it really makes you wonder, right? What other wobbly problems are out there, just waiting for us to look at them in the right way?